All right, so moving on to our next section. Under Unit 7, Inference of Quantitative Data, means, we're looking at means here because we've already done proportions. We're moving on to Section 2, which is looking at the significant tests for means. Okay, so we're looking at testing for significance, which is when we do our null and alternative hypotheses for these. So we talked about the t-value and all that stuff already. So when to use a t or a z? When we know the population standard deviation, we use a z. If we do not know the populations, keyword there's populations, standard deviation, then we use the t. So if you're told the sample standard deviation, then you are using a t test. Okay, so the standard deviation is the key part here with deciding between a z and a t. Okay. All right, so underneath state, okay. So remember for state, when we're doing our hypothesis tests, so our null hypothesis, our h sub 0 is the mu is equal to mu 0, whatever is the stated mu value. Okay, so the mu is equal to 12, the mu is equal to 13, whatever is stated. And then our alternative hypothesis is where we test our claim. So this is what's going to be either mu is greater than, mu is less than, or mu is not equal to. Okay, so those are your three options: is greater than, less than, not equal to. And it all depends on what is said. Okay. Also in state, define the parameters. So you want to say what mu is, so what's the context of the problem, and then mention what the level of significance is. So the alpha level, alpha 0.05, alpha 0.1, alpha 0.001, whatever the alpha is. So make sure you state that also in the state section. Okay, so that first part. Next up is our plan, which is the random, independent, and normal. So for this is a significance test. So under random, you just want to mention if it's a random assignment or random sampling, SRS. Is it independent? So one data point doesn't affect the other. That would be if you're talking about an experiment, the 10% criteria, or the 10% condition, if you're talking about the sampling of it. That's for independent. Under normal, you are looking at if it's more than 30, then it's safe to do a test because of the central limits theorem. Okay, so CLT, you're able to do it. If it's less than 30, then you want to look at the dot plot, look at it, look at the general shape of it and see, does it fall into a kind of a normal curve? Is there no outliers, that type of stuff? Or if it even states that the population is normally distributed, then you could say that the sample would be as well, and that falls under normal. Okay. If any of those criteria are not met, remember you write proceed with caution, but you continue on. And you mention, hey, it's less than 30 and there seems to be some outliers. Proceed with caution. So it might not be normal. You know, the 10% criteria wasn't met. Proceed with caution. Okay. But you still continue on. You don't just stop there. Okay, under do, so doing your test statistic. So you take your statistic, your value that you found, the X bar, in this case, the mean that was found. You subtract it from the parameter, which is the number that you put in your null hypothesis. So whatever you put in your null hypothesis, that goes here. And then the bottom is the standard deviation of the statistic. Okay, so it's the standard deviation of the statistic, which is your mu, or not mu, sigma over the square root of n. Okay, so sigma over the square root of n. Make sure you draw your curve because they want to see, make sure you know if it's above or below wherever your bounds are, or on both sides. So you just do a quick curve, you draw this is where my bound is, etc. Okay, these two bullet points here are for your calculator. Okay, so stat test on the TIs, stat test, normal CDF to find the p-value for a z, and then a t-CDF to find the p-value for the t. Okay, and things that you type in, you're typing in what the mean was from what's the stated mean. You're typing in the X bar, the standard deviation, and the n, and then what's your second one. So you're basically doing it all in your calculator, and it can tell you what the p-value is for it, okay, if you wanted to find it on your calculator. But under this, you need to have at least the setup. You need to show the formula for it. Yes, you can use the calculator to find the p-value, but you need to have the setup, okay? They need to see that. Okay, under conclude, because the p-value of blank blank is bigger or smaller than the level of significance, we reject or fail to reject. So remember, if the p-value is smaller, or if the calculated value is smaller than the p-value, then you reject. If the calculated value is larger, or if the p-value is larger than the alpha, then you fail to reject. Okay, and we do, and you're not convincing, yada, 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 and you use context. So you just write it out and make sure you mention your p-value, make sure you mention if it's bigger or smaller than the level of significance, and reject or fail to reject. All right. Okay, let's do some examples. All right, so this example is about AAA batteries. You can go through and read it. Okay. Lasts longer than a regular, yada, yada, yada. Their regular ones last 30 hours of continuous use on average. An SRS of 30 were taken. They lasted 33.9 hours. Standard deviation of 9.8. Okay, so a standard deviation of 9.8. This standard deviation is mentioning that it is from the sample, not past of whatever it is. It is the sample standard deviation. Okay, so you're going to be using a Z or T. It would be a T. So you're using a T in this case. Okay. Do you have level of significance, yada, 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 at 1%? Okay, so 1%, so that means our alpha would be 0.01. Okay, so there's the example that we have. We're going to run through this one, and then we're going to run through another example, and then we'll be done. So here we go. State. So under state, we have to talk about our variable, and we need to mention our null and alternative hypothesis and the level of significance. So the variable is mu, which means the battery life. Okay, it's the average battery life. Our null and alternative hypotheses, we would say that it is equal to 30 is our null hypothesis. Mu is equal to 30. Well, our alternative is that it's greater than 30. And the reason it's greater than 30 is because it mentions that the company thinks that their batteries have a longer life, larger, more than 30. Alpha 0.01, or 1%, okay? Or 0.01 if you want to write that way. This means it's a one tail, so it's just going to be looking at that top side. Okay. Also here you can mention the mean, standard deviation, and the degree of freedom, etc. So the mean was 33.9, standard deviation was 9.8, and n was 30, which means the degree of freedom would be one less, which is 29. Okay. Under plan, so we have our random. It mentions that it's a random sample that was taken, so SRS is hit, marked off. Is it independent? We would assume that 30 is less than 10% of all the batteries that they have. And normal, 30 is greater than or equal to 30. So therefore, we could use CLT. Okay, the central limit theorem can apply to this, and we can say that it is approximately normal. Okay, so there's all those are hit. All right, moving on to do. Okay, moving on to do. So because it is a t-test, that means we are going to use a t-distribution. So here's our formula. So this is what we want to write out, is up here. Okay, write out what formula you're using, or state which formula you're using. Okay, So we're using a t, x bar minus the mu all over sx all over the square root of n. Okay, and plug it all in. Do it piece by piece, unless you could do it all in your calculator at once. But I have a feeling you guys can't do it all at once. If you drop a parenthesis, you'll get a wrong answer. This calculated through gets us 2.18. Okay. Okay, 2.18 is the value. Okay. From here, we're going to use the TCDF of 2.180, comma 1E99, comma 29. And that will get you what your p-value is, which is 0.0188. Okay. Okay. This part you don't need on the AP exam. Okay. You do this on your calculator, don't write it out, because they're assuming that you're going to do it for your p-value. Okay, especially for a t. So if this was our p-value, our alpha was 0.001, it was a one-tail. Okay, we also want to draw our image here, so we want to draw our curve so we can see it. It's in the top half. And we would say that because the p-value of 0.0188 is larger than the alpha of 0.01, we would fail to reject because the p-value is larger than the alpha. So we do not have convincing evidence that the battery life is longer. We don't say that it won't be, we just don't have convincing evidence. Okay, that's the key thing here, is that we're not confirming that it's equal to 30. We're saying that we don't have enough evidence that it is more than 30. Okay, it's a key thing here. All right, so that is that example. Now, let's move on to another one. Okay. Okay, so here's another one where you're given your numbers. Again, you're going to want to use your calculator. L1, use your list. So L1 is your list, and then find your mean and your standard deviation. Again, standard deviation, use SX. Don't use sigma x. Use SX. That's the one that you're using. So this is about dissolved oxygen in your bloodstream, measured in milligrams per liter, 15 random, not your bloodstream, in a river. 15 random spots were taken in a stream. And basically they want to see if it's below 5, things can die because there's not enough oxygen in it. And so they want to see, is it less than 5, essentially. Okay. And so alpha 0.05 does it put at risk. So take a second, you can work through this one. You can pause it. Okay, so let's move on to state. So state, we are going to be looking at our values. Okay, mean, the mean of this, so mu is equal to the dissolved oxygen level in the stream. Okay, and then our null and alternative hypothesis is that it's equal to 5, because remember the null is always equal to 5, while our alternative is going to be less than 5. Okay, so our alternative is less than 5 because we want to see it's the animals at risk. Alpha was 0.05, so we get a one tail with an alpha 0.05. Underneath plan, we go through each one by one. Is it random? Yes, because they were randomly chosen, so it was a random sample. Is it independent? 15 is probably less than 10% of all the locations in the stream. And if you plot that in a box and whisker plot, it looks fairly normal. There's not really, there's no real outliers on it. Okay, so if you just graph the box and whisker real quick, you can have it, which again, your calculator can do that as well. Second y equals, set up the graph for a box and whisker, and your calculator is able to do that as well, and you can graph it. Okay, so all the criteria are met. We're pretty good. Moving on to the next one, we're on to do. So do, since this is less than 30, that means that, and the standard deviation is not given, the population standard deviation is not given, that means we have to use a t. So we'd use a one sample t-test for means. So we have our formula. The average ended up being about 4.775. and the standard deviation was 0.939. So 4.775 minus 5 all over 0.939 all over the square root of n. Okay, from there we solve it, we get down to negative 0.927. So we would again want to draw our graph, okay, so we can see it, and then we see the bottom half of it. From there, calculate the p-value, which again is from your calculator. Okay, we'll be able to tell you your p-value fairly easy, is 0.185. Remember, our alpha was 0.05, so this is almost 4 times, over 3 times, but not 4 times larger than it. So that means that we would again fail to reject this. Okay, we do not have convincing evidence of that the aquatic life in the stream is at risk. So we look at it and go, that's okay, no problem here. Yeah, the average was lower, but it's probably not overall the average is lower than 5. Okay, and that's what we would do for our conclusion. Okay, one last thing with this. So in the previous example, if we looked at it and we want to talk about our type 1, type 2, so you could get a question that goes, okay, in this example, describe the difference between a type 1 and a type 2 error in the process. So this one was talking about the aquatic life, okay, and if it's lower than 5, then they are in trouble. They're at risk of dying, essentially, if we want to be blunt about it. If it's a type 1 error, we would say that the aquatic life is at risk when it isn't really at risk. So this is when we would say that we rejected the null hypothesis when we shouldn't have. Okay, so we reject the null hypothesis when we shouldn't have. That is your type 1 error. If you remember the box that we made with type 1, type 2, and power and everything. So a type 1 error means that we rejected the null hypothesis, but we shouldn't have. And so in this example, what we would do is that we'd go, oh, the fish are in trouble. We got to save them, when we didn't really have to save them. Okay, so we basically, we waste resources when we didn't have to. Okay, now, saving fish, you might go, we're not wasting resources, we're making their life better. That's fine. Okay, but when a company or a government is thinking cost-wise and they don't want to waste money on something that they don't have to, that's where the type 1 error comes into play. Your type 2 error is when you have your, is when we fail to reject it when we should have rejected it. So this example, we failed to reject it. Okay, we failed to reject, and we basically said, nah, fish are fine. The mean's not below 5. It's, you know, just our sampling is a little less. Well, because of that, we are putting them at risk because they might actually need our help, but we're going, no, they don't need our help because our statistics say that. That's the type 2 error. So looking at this, you go, okay, well, which one do you think is worse, wasting money or wasting fish? That's up to you. I personally would probably say the type 2 error is probably worse in this situation. So that's just how it would be with your type 1, type 2. So again, type 1 means that you rejected the null hypothesis when you shouldn't have, and a type 2 is when you didn't reject the null hypothesis and you should have rejected it. Okay, and so that's the example. So this, if anything, this example would have fallen into the type 2 because we failed to reject it and we said it's not lower than 5, and it might actually be lower than 5. All right, that's the end of section 2, and we are done. See you in section 3.